This is your presenter Asloob Mudassar, and I am presenting slide number 89 of the course on laser physics. Question is, give a detailed analysis of the field inside a two-mirror resonator as a standing or traveling wave. Also signify the meaning of LMN subscripts. The answer is, following equation number 81.5 and equation number 81.27, the field inside a two-mirror resonator can be written as E prime LMN of XYZ is equal to W naught over W HL of 2 square root of 2 into X divided by W, then HM of square root of 2 multiplied by Y divided by W, then E to the power minus X square plus Y square over W square multiplied with E to the power minus iota K X square plus Y square over 2 capital R, and then multiplied by E to the power minus iota KZ plus iota phi LM, where phi LM is equal to 1 plus L plus M, this term in parenthesis multiplied by phi. You see that here I am mentioning the two equations given in question number 81.5 and equation given in question number 81.27. So it means that you should consult slide number 81, because I am mentioning some formulas and some equations taken from that one directly, because these equations have been explained there. So I am just borrowing those equations from the slide number 81 and just mentioning them. It is advised you consult those relevant documents, for example, especially slide number 81. So you see that this is the field, that is E prime LMN of XYZ is the field, which is a field inside a two-mirror resonator as a function of XYZ, and LMN are the subscripts that will be explained soon, and where phi LMN is equal to 1 plus L plus M, this whole term multiplied by phi. So if we introduce time dependence into this equation, then the field can be written in the following form. You see that in equation number 89.1, you will notice that there is no time dependence on the right hand side and also on the left hand side. Because if there is a time dependence, then E prime of LMN will be written as a function of X, Y, Z and time t. But you know that this is independent of time. It means that we are discussing this E prime LMN of XYZ as a profile of the wave inside a two-mirror resonator. So if you want to introduce the time factor, you can multiply it with two possible terms. One is that you can multiply on both sides with e to the power iota omega t or e to the power minus iota omega t. So in equation number 2, you are writing on the right hand side E prime. This E prime is the same as E prime of LMN XYZ. But you know that I am skipping off the subscripts LMN and also not writing XYZ. So just E prime is actually the left hand side of equation number 1, and then I am multiplying it with e to the power iota omega t and is labeling it on the left hand side with another electric field E. So this is the complete electric field. Actually, it means that this is a traveling wave because it has now a dependence of time. But you know that as mentioned, there are two possibilities. We can introduce e to the power iota omega t, and the second option as given in equation number 3 is that we can introduce e to the power minus iota omega t. In one case, the traveling wave will travel to the right hand side, and in other case it will travel to the left hand side, which we shall see soon. Let us consider only the longitudinal phase factor in the last two equations, in which we can write So you see that this term, which is e to the power minus iota kz plus iota phi lm, we have declared this term as the longitudinal phase term. And this term has been explained in slide number 81. So I am not going to do any discussion on that one. I am now, you see that this now is contained in E prime in equation number 2 and in equation number 3, because E prime in both these equations is actually this whole expression given in equation number 1 on the right hand side. And also you see that, okay, so I am just going to discuss e to the power minus iota kz plus iota phi lm. The rest of the quantities I am not going to mention because these are not concerned here. So I am just writing that the field is proportional to this quantity, that is the longitudinal phase factor, and also e to the power iota omega t. So now I can combine these two phase factors and I can write that E is proportional to e to the power iota minus kz plus omega t plus phi of Lm. And I am writing it as equation number 2a. And similarly, I am writing equation 3a as E proportional to e to the power iota minus kz minus omega t plus phi Lm. So you see that I have a plus sign with omega t because I have a plus sign in equation 2 with omega t. Similarly, I have negative sign in equation number 3a because in equation number 3 I have e to the power minus iota omega t. That is a negative sign. So E in both in equation number 2 and equation number 3 will now be called as equation 2a and equation 3a. So I have written them in the form of a proportionality. That is, E is proportional to the e to the power iota minus kz plus omega t plus phi Lm as in equation number 2a, and the third, and according to the third equation, that is, for example, according to this equation, I am writing E is proportional to e to the power iota minus kz minus omega t plus phi Lm. During propagation, the phase of the traveling wave stays constant. As you know that this is the basic formulation of a wave, that is the phase has to be constant when the light will when the wave travels. So I am writing the phases of these one to be constant from equation number 2a and equation number 3a, which will be respectively called as equation number 2b and 3b. So for the equation number 2b, I have a minus kz plus omega t plus phi of Lm is equal to constant. And from equation number 3a, I am setting the phase to be to set equal to constant, and then I have minus kz minus omega t plus phi of Lm is equal to constant. Now I am going to explain these two constant phase factors. So let's concentrate first on equation number 2b. So in equation number 2b, you see that there is a plus sign with omega t. So when the time will lapse or when the time will passes, what will happen? This term omega t will increase with the time. But you know that in order to keep this term in the parenthesis to be constant, then you see that this term, that is minus kz should decrease. So the sum of minus kz plus omega t should be equal to constant because phi Lm is already assumed to be constant here. So it means that z should travel in the positive direction, because if z is increasing positively, then this whole term, which is minus kz, will be decreasing. And this decrease will compensate the increase in the term omega t due to the increase of time. So it means that z should increase in the positive direction, which means that this term states that z is moving in the positive direction. It means that this wave shown in figure 2a is moving in a positive direction along the positive z direction, or it means that the equation 2 shown over here is the equation in which the wave is moving towards the positive z direction. Now let's consider the equation number 3b. Here you see that there is a negative sign with the omega t. So it means that when the time will increase, then this term minus omega t will decrease. So in order to compensate this decrease, z should increase in the negative z direction. So that z increases in the negative z direction, which means that minus kz will become a positive quantity. So then minus kz minus k times z due to z propagating in the negative z direction, this term will increase and it will compensate the decrease in the term minus omega t due to increase of time. So the term in the parenthesis will remain constant. But you know that this constant requires that the wave should travel along the negative z direction. It means that in the equation 3a, this electric field or this wave will travel along the negative z direction. And similarly for the equation 3, where we have written E is equal to E prime of E to the power minus omega t, it means that this is the traveling wave which travels in the negative z direction. So now we have understood that if there is a positive iota omega t, it means that the light will travel, that the wave will travel along the positive direction. And if there is a minus omega t, as shown in equation number 3, it means that the wave will travel along the negative z direction. So these two are the traveling waves. One is traveling along the positive z direction, the other is traveling along the negative z direction. So let me read the statement over here, this paragraph. Equation 89.2b states that the wave is traveling along positive z-axis, whereas the equation number 89.3b states that the wave is traveling along minus z-axis. Thus, equation number 2 represents a traveling wave along the positive z-axis, whereas equation number 3 represents a traveling wave moving along the minus z-axis. The standing wave in the resonator can be visualized as the sum of these two oppositely propagating traveling waves. That is why we can write that E is proportional to the E prime cos of omega t. You know that as stated just now that the equation number 2b and equation number 3b states that the wave are traveling along the positive direction and along the negative direction respectively. That is, we have these two waves that is shown in equation number 2 and 3. These waves are traveling along in equation number 2, the wave is traveling along the positive z direction, and in equation number 3, the wave is traveling along the negative z direction. So when these two waves will travel, then you see that these two waves will form standing waves within the cavity. Individually, they are the traveling waves, but when they are combined or superimposed, they will form the standing waves. So if you add these two waves, what will happen? For example, if you add, so rest of the terms are common. You know that in the E prime and E prime is existing in both of these equations. So these are the common terms. The only different terms is E to the power iota omega t and E to the power minus iota omega t. So if you take the superposition of equation number 2 and 3, the rest of the terms on the right hand side, except the time dependent terms are constant, we can take them common. So we have the two terms e to the power iota omega t will add to the term plus e to the power minus iota omega t. And you know that these two terms will add together to give you cos of omega t. Though there is a factor of 2 on the with the terms common on these from these two equations, we can multiply by 2 and we can also divide e to the power iota omega t plus e to the power minus omega t divided by 2. So it means that we can write a cos function when these two will add together. So we have written over here that E is proportional to the E prime. You see that I am not writing the equality sign here, the proportionality sign, because I am not writing the factor of 2 over here. So I am just writing that E is proportional to E prime into cos of omega t. So this cos of omega t is what I have explained because it arises because of the superposition of the two traveling waves traveling in opposite directions shown in equation number 2 and 3 respectively. Okay, now we can put the equality sign. So E is equal to, I am writing T2 times E prime, then E to the power iota omega t. Because I am writing only one of the term over here, for example, this term. I am writing only this term, iota omega t, which is traveling along the positive z direction. So as far as this term is concerned, I am writing out a term over here, which is T2 term. And this wave will be traveling along the positive z direction, will leave the mirror 2 and traveling along the positive z axis, where T2 is the amplitude transmittivity of the mirror 2. Because you see that when this when this wave will leave the cavity through mirror 2, then of course it will be multiplied with the T2, which is the amplitude transmittivity of the mirror 2. So this is the wave which will come out from the laser cavity from the positive z direction. The output coupler of the laser of the resonator, which is on the the mirror 2, where the light will come out from that mirror 2, and then you need to multiply it with the T2, which is the amplitude transmittivity of the mirror 2. So equation number 5 gives you the wave which will come out in the form of an amplitude wave from the mirror 2. From the field in equation number 89.1, that is this field we have written, this is the field. So the field from equation number 89.1, it is obvious that the field has explicit dependence on L and M, which determine the order of two Hermite polynomials. One of the Hermite polynomials is x dependent while the other is y dependent. The subscript L determines the field nulls. Field nulls mean that the points where the field is going to be 0. The subscript L determines the field nulls along the x direction, whereas the subscript M determines the field nulls along the y direction. So you can see that L, M, and appears with the Hermite polynomials as a subscript with the Hermite polynomials with HL and with the HM. So you see that these are the two which appears over here. Here we are not talking about the n subscript because we shall be coming to that one later on. But here we have just mentioned the two subscripts L and M, and you know that L, M, and determines the field null. That is the null points where the field is going to be 0 along the s direction, that will be given by the subscript L, and whereas the subscript M determines the field nulls along the y direction. And you know that x and y directions are perpendicular to the z direction, which is and z direction is along the resonator cavity. And you know that x and y are perpendicular to that one. So the plane x and y, so the plane determined by x and y is perpendicular to the z axis. When L is equal to 0 and M is equal to 0, the fundamental mode TEM, and you see that in the subscript we have written 0, 0, because one stands for L, the second one stands for M. So we have TEM 0, 0 as no field nulls along the x and y directions. So you see that this TEM 00 mode is actually the Gaussian mode. And you know that in the Gaussian mode, there are no field intensity nulls anywhere because the Gaussian curve is a continuous curve. It vanishes it vanishes at the two extreme ends, but in between them there are no amplitude nulls. So when L is equal to 0, M is equal to 0, the fundamental mode TEM 00 has no field nulls along the x and y directions, whereas L is equal to 0, M is equal to 1 mode has no field nulls along the x direction, but one field null along the y direction. Because the M is equal to 1 corresponds to the field nulls along the y direction. So since M is equal to 1, it means that there is only one field null along the y direction. And this has been explained in the figure in question number 81.3. You can consult that figure there. The field has explicit dependence on N. The field has implicit dependence on N through the K number. Because you know that in equation number 1, if you see, then you see that N is not appearing explicitly in equation number 1. It means that N has a dependence, that is E prime has a dependence on N, but some implicit way. And this is what we are going to now explain. The field has implicit dependence on N through the wave number K. That is K is equal to 2 pi into nu LMN over C. where nu Lm is the resonance frequency. And you know that this resonance frequency now depends upon the three integers L, M, and N, where nu Lmn is equal to C over 2L, and within the parentheses we have n plus phi of Lm divided by 2 pi. This nu Lm is the mode frequency. And you know that these if many nu Lm are oscillating within the laser cavity, then of course it means this will give you the number of longitudinal modes in the cavity or in the resonator. Here n is the number of half wavelengths that fit in the cavity length as the standing waves. That is, capital L is equal to n times L by 2, lambda by 2. You see that this is the equation. We have also discussed this equation before. That is, in a cavity of length L, integer number of half wavelengths will fit into the cavity. And if many wavelengths satisfy this condition for different value of n, then it means that different longitudinal modes are possible within that cavity. So n plus 1 thus gives the number of field nulls along the z direction. That is, n plus 1 are the number of points at which the field will be null, that is, the field is going to be 0 along the z direction. Equation 89.1, that is the following equation, explains the concept. You see that you have two mirrors M1 and M2. The cavity has a separation, or the length of the cavity is capital L, and you know that n is equal to 6. Which means that you can notice that how many standing waves are being fitted into this region. 1, 2, 3, 4, 5, 6. So that's why we have n is equal to 6. Because if you put n is equal to 6, it means that you can put 6 number of half wavelengths. That is, complete wavelength will be 3 in the number, or half wavelength will be 6 in the number. And you can see that these are 6 in numbers, or full wavelengths are 3 in the number. And you can see that the field nulls are 7, that there are 7 points in this standing wave pattern where the intensity is going to be, where the field is going to be 0. For example, this is point number 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. So there are 7 field null points along the z direction in the cavity of length L when n is equal to 6. So the number of field points is always 1 greater than the value of 6. For example, as we have stated over here, that n plus 1 thus give the number of field nulls along the z direction. This is what we have explained in this diagram. And the caption of the figure is standing waves within a resonant cavity with n is equal to 6 and with field nulls equal to 7. So I have answered all the queries made in the question. So this completes our answer. So this is the end of slide number 89.